Project 3.6 AVR Assembly Dabble by Atticus Stiplady. The purpose of this project is to take the code written in previous classes, merge them together, and write a double-dabble algorithm that will create a timer interrupt every 1 second, read the analog voltage from a potentiometer on pin A5, take that decimal value and convert it to BCD using the double-dabble algorithm, and then display it on the serial monitor. Project 3.3 AVR Assembly Traffic Light helps explain the basics as to what the assembly language is and how it works, in contrast to other high-level coding languages such as C++ and Java. The timer interrupts, which are key in letting the program know when to read the analog values found on pin A5 in assembly, allow the microcontroller to automatically execute specific blocks of code when the timer, in this case 1 second, reaches a certain condition, such as an overflow. Interrupts are handled using an interrupt vector table referred to as the IVT. This table will associate each type of interrupt with a memory address of its corresponding interrupt service routine, ISR. In the case of the program, the timer 1 overflow vector label marks the ISR that runs when timer 1 overflows. When the overflow occurs, the microcontroller automatically jumps to the code at this label, executes it, and then returns using the RETI instruction, which safely resumes the main program. The equation listed is how the program is able to obtain the baud prescaler from the inputted baud rate, with the OCS representing the clock speed of the circuit, 16 megahertz for the Arduino Nano, baud being the inputted baud rate, 9,600 BPS for this example, and UBRR being the USAT baud rate register, which determines how fast it is sent/received. By subbing in the values and executing it, the resulting prescaler value is equivalent to around 103.1667, rounding down to 103. The double-dabble algorithm is key within the confines of this project, as it is the algorithm that takes the stored analog value from the potentiometer on analog pin A5 and converts the 10-bit binary number into a BCD value. The algorithm works by first taking the inputted binary value and placing them in registers, most commonly R18 and R19 for simplicity, and begins by bit shifting the value of 1 bit at a time into a group of BCD digits by pushing it into increasing registers such as R20 through 22. Once shifted, the moment one group of BCD values has reached a binary value that is or exceeds 5, 3 is added to it. This add 3 step ensures that the digits stay within the range of a valid decimal numbers 0 through 9 as the binary value is gradually shifted in. Following the addition of 3, the new binary value that is found within a specific register is then ignored and immediately shifted, even if the binary number is above 5, to ensure that the algorithm does not loop in place. This process will continue however many times until the number of shifts is equivalent to the bit value of the inputted binary value, / when the number reaches the corresponding BCD value. The reason this works is because the BCD uses 4 bits to represent each decimal digit, e.g. 0001 for 1, 1001 for 9, and the algorithm accounts for the difference between the binary and decimal structure. The last portion of this project has to deal with something referred to as a serial monitor, a built-in tool within the Arduino IDE that enables real-time communication between a computer and a microcontroller board. Similar to those such as an Arduino Nano, the serial monitor has been used in previous projects as a stepping stone to verify calculations that are being performed, and can also be used to refer information about the internals of a program to the user in any format, whether that be binary or gray code. The serial monitor functions as a digital terminal window, allowing anyone to both view the output from a microcontroller and send input commands to it over a USB connection. While most commonly being used for high-level Arduino C functions, the serial monitor also has the ability to be used in AVR assembly by writing directly to and reading from the appropriate hardware registers, which provide finer control and insight into how the hardware actually handles data transmission. The code begins by including the necessary files to access the names for the I/O ports, and then declares each register as specific names, such as register 18 and 19. The section immediately follows the declarations and placements by creating the main label and calls a setup of things such as the I/O ports, time 1 overflow, USART, etc. Following that, the hold label is created and set so it is an infinite loop where the circuit repeats, waiting for the interrupts. Following that, the double-dabble is set as 16-bit shifts are required for the algorithm. Following that is the main body of the algorithm, as it is the loop that will consistently shift and compare the values, deciding whether a shift is required or an addition of 3. This is repeated and must be checked for each register after the first initial 9 shifts. After that, the setup functions, which were defined earlier in the code, are declared. The last main section of this code deals with the display label, in which each of the characters is displayed through the UART. As this function goes through, each character in the register is individually sent and appears to be combined, finishing the program. This will repeat every 1 second, displaying the analog value of the potentiometer. Thank you for taking the time to listen to my video on Project 3.6 AVR Assembly Double Dabble.